Hello my dear students, welcome to the session. Myself Ravi Bogdula, faculty for GATE Computer Science. So in this video, I would like to discuss one of the most important topic from the operating system, that is semaphore. So this semaphore concept we'll learn, as well as we'll see some previous year GATE questions which were asked on semaphore based. So now let's start the session. Before starting of the session, so I would like to recommend all of you try to subscribe our YouTube channel so that you will be getting the notification for the upcoming videos. Now let's look on semaphore. So what semaphore it says? You might have studied various synchronization mechanisms like lock variable, strict alternation, Peterson solution, TSL instruction. You understand semaphore is one of the practical implementable algorithm for IPC environment. In a concurrent environment where you want to ensure the mutual exclusion to access the shared code or shared resources, so semaphore operations can be used. Hence definitely it is ensuring the mutual exclusion. Or else you understand under multi-threading area, so when you created multiple threads and if you want to control some threads, like some threads only you want to allow to run in a concurrent manner, so you can use the semaphore operations to control it. Like this various practical applications you can see on semaphore. So coming into the topic here, this concept was proposed by, you understand, E. Dijkstra. It is an operating system resource. When I say operating system resource, it must be implemented in the kernel part. Then hence I can say it is an atomic nature. Means the semaphore is a blocking mechanism and it supports the multiple processes. What is blocking mechanism? So there are some mechanisms which are like attempted to implement the IPC environment which are non-busy wait, like busy wait mechanisms. But this semaphore comes under, so non-busy wait mechanism is a blocking protocol, blocking mechanism. You understand? It is using these system calls, blocking system calls like the sleep and wake up. So now CPU time is not wasted when I use a semaphores. Suppose if you take up the synchronization mechanism, TSL instruction Peterson is there. So which are ensuring the mutual exclusion, but which are those two algorithm comes under busy wait mechanism, it's substantially wasting the CPU time. So when I go for semaphore, it is a blocking system call, it is using the various blocking system calls like sleep and wake up. So the CPU time is not wasted. One process using other process may be in a block state. And it is supporting multiple process solutions at user mode application, you can say. So Dijkstra has proposed two operations for semaphore. These operations are carried out in the kernel mode only. What are those operations? The operation you understand, down and up operation, or we can say P operation, P or wait. So either down or P or wait, all you can use, one of them you can use it, all are same only. You can use up or V or signal. So these are the another type of operations you can say, either you can use up or V or signal. So basically two operations. So what is the meaning of down operation, understand? When I say down operation, so down is carried out on semaphore variable, you see. So its down indicates what? Decrement the current value of semaphore, it says. What is up indication? Is increment the current value of semaphore. So that means understand the semaphore is basically a variable. Semaphore is basically variable. When I say it is a variable, variable must be associated with some data type. So which data type? Having same. Semaphore is a variable of semaphore itself and having takes the integer values. It takes only integer value. Based on this integer values to understand, based on this integer value, semaphore is classified into two types. One is counting semaphore, other is binary semaphore. Please understand. I repeat my statement. Semaphore is nothing but variable of semaphore itself, so data type, and takes only integral values. This based on the integral values, the semaphore is broadly classified into two categories. One is counting semaphore, other is binary semaphore. Now let's understand each one of them clearly. The how counting semaphore being implementable, then how binary semaphore can be implementable, how this semaphore operations can be used in a IPC environment. So that will be discussed detail. So first we will move on to the first counting semaphore. We will move on to the counting semaphore. So now as I mentioned, counting semaphore takes or binary semaphore takes integer values. So counting semaphore starts from, it takes minus infinity to plus infinity. All this integer comes under counting semaphore. The binary semaphore takes only 0, 1. Only two values are associated, that is 0, 1. So this counting semaphore takes minus infinity to plus infinity. So now let's see its implementation, this implementation. So now I'll be using the structure, struct semaphore, and this structure members are, one is value, int value. So int value. So this defines, the current value of semaphore. This defines the current value of semaphore. So followed by another type. So there is a L, I am defining L. L is a Q, understand, Q. This is a Q. Q type I am taking as a data type. So L is a Q. Okay. So what is this Q is containing, understand, Q. This, the L is a Q. The LQ is containing the list of blocked processes. It is containing list of blocked processes. Okay. So what is the meaning of blocked processes need to be understand. Okay. Suppose when I use this semaphore variables, so during execution of, please understand, during execution of down operation, if the operation is unsuccessful, the particular process need to be blocked. The blocked processor we are keeping in. So what is L? L is a Q. Q contains list of blocked processes while performing the down operation especially, but the nature of unsuccessful operations. So we need to understand what is a successful and unsuccessful operation is clearly. Okay. So this is structure, you see. This is there are two members will be there. So one is the value, current value of semaphore is defined by this one, and another is what? Is the Q contain the list of blocked processes. So let's understand in clearly. Now look this. So in a practical scenarios, we'll be using this semaphore operations. How, sir? Suppose some code is there in a code, wherever critical section, suppose here is a critical section, okay, critical section. For this critical section, I want to ensure the mutual exclusion, means no two process should go inside the critical section at a time. For this, I would like to use semaphore variables here. So first of all, I am defining the semaphore, okay. So semaphore, so S is a semaphore, please understand, S is semaphore. I said S is a variable of type what? Semaphore type only. S is a semaphore is a, I said is the variable of which type? Semaphore type only. So I am assigning some value, S dot value. So we know how to access the structure members. S dot value, let's take I am defining as some 3 assumption. So I may be operating some semaphore operations. I said now we have operation down on S, I may be using like this, followed by critical sections, and I may using like up of S here, up of S, and followed by other code will be there like this. Meaning in IPC environment, in a concurrent environment, wherever critical section is there, the critical section should be enclosed with the semaphore operations. It is not compulsory, the first is the down operation, next is what? Up operation. It can be placed any order based on the requirement of the particular environment or application. It can start with the down operation, maybe start with what? Up operation also, based on our requirement only. I said basically we have two types of operations we have. One is down, other is up. We'll understand details of the down and up here. Okay. So usage in the application will be like this. Wherever shared code is there, the shared code should be enclosed by what? Semaphore operations here. So I hope you understand this part here. Now look at the structure, this architecture of any synchronization mechanism. We know, suppose here is a critical section, if you take this critical section, okay, look this. And for this critical section, there is an entry section will be there, entry section, okay, entry section, this entry section, use the critical section. Then once usage of critical section is over, the followed by what will be there here? Exit section. This is what? Exit section, okay. Now definitely race condition will be there. N number of process can try to enter the critical section. So N number of process can try to enter in the critical section, but entry section must be ensure only one process is allowed to use the critical section at a time. So that is the various synchronization mechanism can be deployed here. So we are looking for what? Semaphore. As I mentioned, usage of semaphore will be what? Semaphore operations need to be enclosed, right? So let me suppose I'm using what? Down operation here, down, okay. So down on, what? Semaphore variable S. So once usage is over, I'm performing up of S here. I'm saying it is not necessary always the starting with the down operation or ends with up operation. It can be start with the up operation also, based on what? Requirement of the application only. Now, let's take this as scenario. Now look at the point here, okay. So one thing we need to notice here, this semaphore structure, there are two members are there. The value of semaphore followed by is a queue, contains the data structure, contain the list of blocked processes. I said blocked process. So what is the list of blocked process? When we say the process blocked, when a particular process is carried out the down operation semaphore, if the results of the semaphore is a negative, we can say what? Unsuccessful operation, otherwise successful operation, like this. So I mean to say we should understand what is successful and unsuccessful operation here. So let's understand that part clearly. So I'll be taking the scenario again. This is an entry section to the what? Critical section. So entry section. So race condition is there, n number of processes trying to access. Let's take process P1 trying, and process P2 also trying, and process P3 also trying, suppose on. So look at here. Here is a critical section. Now. Okay. Entry section, critical section, followed by exit section. Exit section is there. At the entry section, I am using the down operation, down on this semaphore S value. Okay. At exit section, I will be using the up operation, up on S here. Okay. Let's understand. So initial value of semaphore S dot value of just I am considering 3. Okay. Let's take this is a critical section enclosed by 2 operations, down followed by up operation. Suppose at time T0, understand, okay, under multi-programming or concurrent environment, this ready queue right now having how many processes? P1, P2 and P3. Okay. So 3 processes available, because 3 processes raising to access the critical section simultaneously. So as per the scheduler sub at time T0, suppose process P1 is scheduled assumption. Okay. Process P1 is scheduled. So what process P1 does now? It perform the down on S. So we can also write P of S also. We can write P of down on S. What is the down indication? I mentioned down indicates the decrement the current value of semaphore. Down indicates decrement the current value of semaphore. What is S value currently? 3. So after this one, what happens? S value becomes what? 2, decremented. After decrementing, please, after perform the down operation, the semaphore value is positive, please understand, non-negative, positive. That means successful operation. So this means what? Successful operation. If I say successful operation means the process is allowed to enter the critical section. Now you understand. So process P1 is entered. Enter into critical section here. Let's say when process P1 is running, after some time, let's take, after some time at time T4, preemption is occurred assumption. So now process P1, so process P1 in critical section, right? Process P1 in critical section, running like this. Suppose a preemption is occurred. So during execution of critical section, so preemption is occurred. At time T4, suppose I schedule what? Process P2, okay. So process P2 also will run the what? P of S. What is the meaning of P of S? Down of S. What is the down of S? Decrement the current semaphore value. Currently semaphore value is 2. If I decrement it, what? S value becomes what? 1. So this implies what? Again it is a successful operation. Is it not? Successful operation. The successful operation meaning what? You can allow process to enter into critical section. So process P2 also entered here. So process P1 was holding the critical section, came out of the CPU, correct or not? Now process P2 enter into CPU using the same critical section now here. That's the meaning of successful operation here. So now process P2 is running the critical section, right? Process P2 is running the critical section work. The critical section has set of instructions, right? Set of instructions. During this execution, suppose preemption is occurred. Then after some time, like a time T8 assumption, so maybe process P3 scheduled, process P3 is scheduled now, process P3 scheduled. So process P3 also will run what? Down on S, right? Down operation is that down on S will perform. What is the down on S indication? Decrement it. So decrement the current semaphore, S value, current semaphore value is how much? 1. So if I decrement what, S becomes 0. So S value 0. This still positive, you understand, is a successful operation. Successful operation, okay, it is also successful operation. I hope you understand. S equals 0, it is a successful operation now. That means, so process P3 also can enter into critical section now. Process P3 can also enter in critical section. Means process P2 was holding the critical section, came out of the CPU, now process P3 has entered. Thus, I am only differentiating now the successful and unsuccessful operation. I am not ensuring, I am not trying to ensure any mutual exclusion. So that we will see later. Right now just understand what is the meaning of successful and unsuccessful. Very simple statement I am telling you. After carried out the down operation on a semaphore value, the result is still positive, that we can say successful operation. So now see, so now process P3, so process P3 in critical section, right? Process P3 in critical section, code is running now like this. Suppose let's take one more process also there, let's take process P4 also there assumption, process P4 also trying to enter. If preemption is occurred during this execution time, preemption is occur, let's take a time T, so 12 I am taking the process P4 is scheduled, so this also will perform the P of S. Currently S value almost 0, so down means what? S equal to -1, so S equal to -1 nothing but negative, so this negative value of semaphore defines the unsuccessful operation. Unsuccessful operation. When operation is unsuccessful, very simply you understand, so now L is what? Q, S dot L, this S dot L, in this S dot L, unsuccessful operation, whichever process involved in unsuccessful operation, the process need to be blocked here. P4 I blocked. So I repeat my point here, you can go and see. The L is a Q type, is a data structure, contain the list of blocked processes. So this blocked processes happen during during execution of the down operation. If it is unsuccessful, we have to block it. So it is unsuccessful, we have to block it. Yes, I block now. If suppose process P5 is straight right now assumption, again it's performed the down on S. S becomes what? -2. S becomes -2. That indicates what? Unsuccessful operation. Then process P5 also need to be blocked rate. So process P5, nothing process P, like no PCB. PCB if you process P5, you need to keep into what? This S dot LQ and block it. For this we are calling what? System call. Which system call? Sleep system call. We are calling sleep system call. I hope you understand the difference between the successful and unsuccessful operation here. So I repeat, successful means what? After carrying out the down operation on semaphore value, the result is positive successful. So that means successful operation means process can enter into critical section. Unsuccessful operation means if the semaphore value is negative after performing the down operation on semaphore, then we can say unsuccessful. So unsuccessful operation process need to be blocked rate in a queue. This is only differentiation you did learn. Now let's move on here. I want to ensure the mutual exclusion. So you can pause the video, you can think yourself, all of you. I want to ensure the mutual exclusion, means I want to allow only one process to use the critical section. So what must be the initial value of semaphore? Let's understand. The structure is same. What is the structure? The structure you understand. So entry section, okay, entry section. We are using the down on, okay, down on S operation. So this is trying, like here is a critical section, followed by what? Up, like no, under exit section, I'll be using up of S. So race condition is there, process P1 trying, maybe process P2 trying, maybe process 3 or n number of process trying to enter the critical section. So n number of process trying to enter the critical section. Let's understand here, initial value of S dot value, the semaphore value is 1 assumption, okay. So later we can understand what is the initial value of semaphore must be there to ensure the mutual exclusion, but I am trying to take what? The S dot value equal to 1. So initially S dot value equal to 1 I am taking. Let's understand now. So there are, so under concurrent environment, now ready queue has 3 process, P1, P2, P3, 3 process available, correct. ready queue has 3 processes, P1, P2, P3. So as per the scheduling policy, one of the process schedule assumption. At time T0, process P1 schedule assumption. Okay, process P1 schedule. So process P1 want to access critical section. The before critical section there is a down operation. So I am writing down means what? P of S I am writing. So when I write P of S, what happens? S value becomes decremented. Currently S value how much? 1. 1 decrement nothing, it becomes 0. So this implication what? Successful operation only. So successful operation only. Successful, right? That means, so process P1 has entered into critical section, right? Critical section. There are set of instructions are there now. During execution of process P1 in a critical section, suppose preemption is occur, like maybe running with a round robin algorithm, time quantum might be expired. So this P1 got preempted. So now at time T4 I am taking, suppose process P2 schedule. So process P1 came to ready queue back, correct or not? It was holding the critical section, came out of the CPU and entered into ready queue now. The CPU scheduler is scheduled another process P2. Now it is also running what code P of S now. P of S is going to run. What is the P of S indication? Down of S. Down of S nothing but decrement the current semaphore value. So this implies, I understand, S becomes what? -1. So -1 implication, what is the implication? Unsuccessful operation. Unsuccessful operation. This implication what? Unsuccessful operation. If the operation unsuccessful, what should I do? You have to block it. You have to block it. I'll be showing S dot L. Okay. So L is what? L is a queue. L is a queue, and it is part of the structure. So now I'm accessing what? S dot L. So process P2 ID you have to block it. Process P2 is blocked now. Process P2 is blocked. So then, when process P2 got blocked, ready queue is available with what? Process P1 and P3. Suppose at time T6 assumption. Okay. So process P3. So process P3 schedule assumption. So now process P3 going to be, so process P3 going to be run what? The P of S. Now P of S. Okay. So what S value currently? -1. So now S value becomes what? -2. This also what? Unsuccessful operation. Then block it. So process P3 also blocked here. Process P3 also blocked here. Now left over with what? Left over with the ready queue. Like how many processes left over with the ready queue now? So process P2, P3 both are blocked here. So left over the P1 only. Let's take example. At time T8, so process P1 came back now. What was the status of the process P1? It was in critical section. Now critical section going to be complete now. The critical section code, what are the leftover code is there? It is going to be complete now. So what we understand right now here? Okay. So first initially process P1 entered into critical section. It was executing. So due to timeout, like it got came out from the CPU, holding the critical section came out of CPU. Now after that P2, P3 not able to enter the critical section, means we ensure the mutual exclusion or not by initializing the semaphore value equal to 1. In this scenario, the initial value of semaphore I initialized 1 so that I want to ensure the mutual exclusion. So only one process I want to allow it. Some scenarios, please understand, I want to allow 100 process to use it. So I can initialize the counting semaphore equal to 100. So 100 process allowed to use it in the computer resources. Like this, based on the requirement, I have to initialize the values. Here I want to ensure the mutual exclusion, hence I initialize a semaphore value equal to 1. Then process P2, P3 got blocked, were not allowed to use the critical section because P1 was in critical section. Hence I can say it is satisfying the what? Mutual exclusion requirement. Therefore I am continuing, now just I am continuing. So process P1 got chance again. So now is enter the critical section, all critical section work is over. Then you have to run what? Up operation, right? Up of S you have to run. Up of S. What is up of S now? Up means what? Up, you understand, up or V operation indicates increment the current semaphore value, increment the current semaphore value by 1. Current semaphore value how much now? So here you understand, I am taking this scenario. S value -2 is there, -2. So you have to make it what? Increment what? S value becomes what? -1 now. So you are not only just incrementing the what semaphore value, it is responsible to the blocker process should be wake up now. Like no, so blocking means what? Suspending, right? The process temporarily suspended from main memory to secondary memory. The suspended process need to be wake up here. Okay. So this during up operation we need to So carried out two activities. First you increment the semaphore value. If the incremented semaphore value is still negative, means there are some blocked process. You have to wake up. You have to wake up. So now to maintain the blocked process, are we using the queue or stack? So if I use stack, what happens? That you understand. If I use the queue, it is ensuring the bounded waiting. Please understand, because the process which first blocked now getting wake up first, correct or not? Because P2 got blocked first. So if I want to wake up, so P2 I have to wake up it, not P3. So to maintain the blocked process, if I use a stack, what happens? Last in, first out. So latest process you are going to wake up. That means what? The process which was blocked earlier is going to be, wait, infinite wait. This we can say weak semaphore. There are counting semaphore of two types, you understand. Semaphore can be implemented two types. So one is strong semaphore, other is weak semaphore. Okay, weak semaphore nothing but bounded wait is may not guaranteed. The strong semaphore always guarantee the bounded waiting. So bounded wait mechanism, this only like the process which is blocked and getting chance first to wake up now. So that's the meaning of strong semaphore here. And we are ensuring the bounded wait by implementing the queue data set, not by stack data set. That is another important point you need to notice. So coming to the point here. So one more point you should observe now. How many successful operations happen? You see, successful operations. How many successful operations happen here? Only one successful operation happen, two unsuccessful operation. So you should understand here. So if I take the before example, here how many successful operations happen? 1, 2, 3, 3 successful. Positive value of counting semaphore always defines, those many successful operations can be carried out. That means, so those many processes can be allowed to use the critical section simultaneously. Means you can allow concurrently. So negative value of counting semaphore indicates or defines those many blocked processes. You can see here is what negative value, how much here? 2, minus 2. Minus 2 indicate 2. 2 indicate the two processes were blocked here during this transition. Two processes were blocked. So positive value how much? 1. The value is what? Initial 1. So only one successful operation can be carried out. See, we have done only one successful operation. So remaining n number of processes tried. So my keep on decrementing only, right? Keep on decrementing, block it only. Any moment of time, negative value of counting semaphore defines those many unsuccessful operations or those many blocked processes in the system. So this is a generalized point you can understand. So I was talking like during up operation here, you have to increment this value and also should wake up. Which process should wake up now? I incremented S value, so minus 1, then I have to wake up what? So process P2 should wake up. So now, so process P2 comes to picture. Let's take a time T10. So I'm writing that this timing diagram also. So timing, so the tracing, the framework you can see, so that sequence of steps I am writing so that you can understand better way. At time T10, P1 already completed. So now P2 came. Okay. So now where P2 will enter, please understand, where P2 will enter. So for P2, it was running the down operation. During down operation only it got suspended, like it got blocked, correct or not. So I wake up nothing but next instruction. What is next instruction? Is it will directly enter into critical section. It will directly enter into critical section. So critical section has set of statements. Critical section has set of statements now. So process P2 run all the critical section work, then it will run what? Up operation upon S. So what is the implication of up operation I said? S value should increment. Minus 1 is there, you have to make it what? 0 now. The second one what? Second operation, if the blocked process still present, you have to wake up. That's what process P3 you have to wake up. So process P3 wake up. At time T, suppose let's take 12. So process P3 came, it will come to where? Directly critical section only, right? Because even process P3 also got blocked during down operation only. After this operation, next instruction nothing but entering into critical section only, right? So now it is also will enter in critical section. So critical section has set of instructions, completes, it performed the up operation. So that means you have to increment S value how much? So 0 was there, you have to make it what? 1. So now second, you have to wake up. We do not have any process to wake up, right? So then I can stop it here. So when I make it S equal to 1, nothing but any new process can try to enter the critical section or not. Can it try? Yes, it can try it. It can try it. Any process can try to enter the critical section because semaphore value is 1. Then, so we should think now how to write a code for a down operation as well as up operation. So just I'm little going back and understand the down. What happened in down during down operation? So we read in the current value of counting semaphore, reading, just you decrementing, we are decremented. If the decremented value is positive, we say successful. If it is negative, we are blocking, correct or not. So I have to do the comparison or not. So S dot value is the current value of semaphore. If it is positive, greater than 0, what should I do? Greater than 0, simply you return. So allow the process to enter the critical section. If it is less than 0, then it is a negative number. So we should what? You should block the process. So this is the what steps we need to write under down operation. So when you think for this up operation, the two works were carried out. What are the two works for the up operation? First to read the like current semaphore value, like no understand. What I can say, first to increment it. After incrementing, this incremented value still less than 0, then we have to wake up the process. You should understand there is some process in the block state, we should wake up. So are we able to understand blocked process or not? How to understand? See, any moment if you see negative value of counting semaphore, negative value of counting semaphore defines those many blocked process. Right now -2 nothing but there are 2 blocked process. Here -1 nothing but there is a 1 blocked process. When it becomes 0, there is no blocked process. That's what directly I made S equal to 1. Yes. So there are no any blocked processes. So this is the observations. So we have to do on this semaphore. Which semaphore we are discussing? Counting semaphore. Okay. So let's write the code for down operation. Suppose down. So down on S, right? Yes. So there's a function call. So function definition I'm writing. This is the semaphore, okay. Semaphore, yes. So I'm receiving this parameter down. Okay. What should I do? Step number 1. So pause the video, you can think yourself. So down operation, what down operation is doing? The down operation simply decrementing the, so S dot value, okay. S dot value equal to S dot value plus 1. S dot value equal to S dot value plus 1. Are you getting my point? S dot value equal to S dot value plus 1, I decremented. So what is second step I have to do? Second step, if, please understand, if this S dot value, okay, S dot value less than 0, right, less than 0, if decremented less than 0, what should I do? What should I do? So this process should block or not? Okay, put this process I am writing, okay, put this process into, okay, S dot L is a Q and block it, So how to block it? By calling what? Sleep function call or not? Else. If it is not happened, definitely you should return it. Return nothing but you come out of the function here, then the process is allowed to enter the critical section. So this is the code for what? Down operation. I hope you understand. So because we have seen the concept, then based on the concepts only, we have written the what? Down operation here. Okay. Similarly, let's write the code for up operation here. Let's write the code for up operation. Okay, up and semaphore, yes, semaphore, yes. Understand? Okay. What is the up? What the up is doing? What we did up cases. So you first of all you should increment the what? Semaphore value S dot, okay, S dot value equal to S dot value plus 1, S dot value plus 1. I incremented. After this incrementing, please understand, if S dot value, understand, still less than or equal to 0, I am writing less than or equal to 0. Are you getting less than or equal to 0? Then you do comparison, right? Or if you write only pure less than, maybe last process may not be woke up. So carefully observe for this. S dot value should be less than or equal to 0. Then what should, if condition is true, you have to pick, select, okay, select a process, okay, select a process from where? S dot L, okay, and you call, which call? Wake up system call, you call it wake up system call, okay. So this, suppose it is greater, then definitely you should else part what? Simply return, okay, return, okay. So this is the up function, you can understand, okay. So this down and up function based on this observations only, you can see first I decremented, how I say successful? So if this value is what? Still positive, then we say successful. If it is negative, unsuccessful. We did the comparison, right? So we did the comparison, right? S dot value less than 0, then you block it, otherwise you return it. This is a down operation and this is the up operation, which comes for what? The counting semaphore. This comes for counting semaphore. I hope you understand clearly the counting semaphore, its implementation part. Okay. So now, so definitely how to use it? Wherever critical sections are there, wherever shared code is there, in a shared code you should ensure like enclose what? Semaphore operations. Now initial value of semaphore value should be depends on the like requirement. If I want to allow more than one process, it should be more than one semaphore value. If you want to ensure the mutual exclusion, so now this counting semaphore should be initialized with what? This is observation, you should note it, correct. So other thing you understand. So how many blocked process present in counting semaphore? How to notice? You just read it, look at the counting value, current counting semaphore value. That will define whether it is a blocked process or unblocked process present. So that you have to notice. Okay. So these are the main observations we have to notice from counting semaphore. In a similar way, we will learn so binary semaphore, its a structure, followed by some problems also we will see. So I would like to continue so this discussion into the part 2, semaphore of part 2. So I hope you understand this concept, all of you. So thank you so much, and also all of you, you understand here.